All right, it's Tuesday, Unit 3, Machine Learning. I have to say that because on Tuesdays I teach three different classes. I want to make sure I'm teaching you the right class today. Otherwise, we'll be taking apart Raspberry Pis and wiring them up. Um, okay, so today we'll just talk about kind of traditional machine learning methods, classification methods, generally. Um, Basically we're taking 20 years of machine learning, so what was like a whole course in machine learning 10 years ago, and we're bringing it all down to this one lecture, and then we'll do Thursday, we'll do some practical examples with it. But we're taking this whole idea of what, all through the 90s and the early 2000s, this is what machine learning was, is what we're going to cover today. And then a lot of this has been superseded by neural networks and AI, what we call AI now, which is mainly neural network, deep learning stuff here. But this is still actually used a lot, especially in industry and that sort of stuff, particularly on numeric data. So anytime you're kind of processing numbers, these are the tools you just kind of pull out and use always for that. So we're going to go over these basic tools here. So I'm going to go into Unit 3, and I've broken these up. Again, these used to be like, I'd have a whole class on each one of these. And so I've kind of brought them down and condensed them here because, again, AI stuff keeps changing so rapidly. I was just looking at the next couple of weeks. I have Unit 5 on convolutional neural networks and Unit 6 on advanced convolutional neural networks. I think this year I'm going to combine those into one unit because convolutional neural networks are important. They're underneath like generative AI, but I want to have a whole week talking about image generation and how image and video generation now works, even 3D generation here. So we're going to have to combine units 5 and 6 together so we can have a new unit 6 on that. Same here when we talk about recurrent neural networks and encoder networks. We're going to have to, I think, combine those again so we have some more room. We have time. We have some work on generative AI and stuff like that. But again, a lot of that, I want to spend more time on this sort of more recent stuff here. So some of this stuff is going. So that's why, again, I've combined what was like 4 units of this class in the past into just this one unit on classical system. So let's go through some of this stuff here. So what is this? What do we mean by classification model? So we have generally some numeric inputs, and then we're going to predict some output, and it's usually a classification. I often think about it as the cat or puppy dog problem, where you have a picture of a cat or a picture of a puppy dog. And again, you're thinking that, well, that I thought you said numeric data. In our world, pictures are numeric data. It's just a bunch of pixels, which are a bunch of numbers. So you have some numeric data here, and then you're predicting a result here, cat or dog here. But maybe in your mind, you're thinking more like, oh, cancer prediction. So like, remember we had the data with breast cancer. We have different measurements, different numbers for every tumor. And then from that, we're predicting malignant or benign, cancer or not. So again, those are our classifications, malignant and benign. And our numeric data is some table of numbers or something like that. So we have so we have some input for every tumor, and then we're predicting that stuff. We also look at iris flower data. Again, we get 4 measurements on each flower, and then we ran it through a model and we predict what type of flower, type of iris that is. So what are some common ways of doing these models here? So often what people think of might be the easiest way, and this is still done sometimes, is the k-nearest neighbor. So here we have data we're plotting out to kind of visualize it. So we just have 2 data points. Maybe we're looking at fruit here, and maybe this is some measure of how smooth or rough the texture is, and maybe this is on the x-axis, and maybe on the y-axis is how big the fruit is, how large it is, or something like that. So we're plotting out two different values here. And then we have some that are green. Let's say the green ones are apples and the orange ones are oranges here. And we have some new fruit. We measure it. We see how, how big it is, how bumpy it is. We plot it. It goes into this location here. And now we're going to try to tell if that's an orange or the apple here. Is it an orange item, or what class is it? And so what we do is we look at the nearest neighbor, just what's nearest to it. That's the one nearest neighbor. And if we look here, then one nearest neighbor, it would be an orange here. If we look at, maybe we don't always want to look at the nearest item. We want to maybe look at the three nearest items. So we might expand our circle out a little bit here, so that we're seeing three items. Let me see where, if I can. So again, if we're looking at just one item here, it's, we expand this circle until we get, here, we start here and we start expanding it out until we get one thing, and the nearest thing is an orange. So it's an orange. But then you think, well, what if we expand it a little bit more? If we expand it a little bit more, then we're seeing, we have 1 vote for orange and 2 votes for green apples here. So then you're thinking maybe it's an apple. And again, if we expand it some more, we'll see we might vote otherwise for this. And again, maybe if we change this thing to a different location, maybe if we, let's say, we can, move this point to 14.5 and move this one to 15.5. If it's over here, it's a little clearer, I guess, here. If I look at the nearest one, it's an apple. If I looked at the nearest 3, they're apple. If I look at the nearest 5, they're apples. So this over here is most likely an apple, a green apple, because all of its neighbors, I have to go pretty wide before I even find one neighbor that's an orange for this classification. So again, that's what we're trying to do is, again, just look at, now, why do we call it K nearest neighbor? Well, the K is just a number. You can talk about the 1 nearest neighbor, the 3 nearest neighbor, the 5, 7 nearest neighbor. You can look at as many neighbors as you want. You can kind of define that. So it kind of depends on how big is your data set. If you only have, 20 things in your data set, like this picture, you might want to only look at the 2 or 3 nearest neighbors. But if you have 1 million things in your data set, you might want to look at the 100 nearest neighbors for this. So the K is in here just as a token and holder for whatever number we want for this stuff. So that's how this works. And so again, if we have some new sample here, this is our iris flowers, a new sample here, we start looking around at the 3 nearest neighbors. They're all these iris setosas, these blue ones. So this is probably an iris setosa. And that makes sense to you here. You see this thing up here, it's all it has is green around it. It's got to be one of these iris virginicas here. Now this is a little harder. It's in this range where it's between the greens and the oranges. So it's a versicolor or a virginica iris. And it's hard to know. So how, again, you might look at the 3 nearest neighbors. 2 of them are iris versicolors. 1 of them's virginica. So you say, well, if 2 out of 3 are this, I'm going to say it's that there for this. So we look at that sort of stuff for this. So that's how this works, is we just look at the nearest neighbors, and we do have to specify the K. So pros, it's easy to understand. It's pretty easy to calculate, fast to calculate. It can be slow on large data sets with millions of things. And the K parameter you have to pick. And sometimes your results change if you pick a different K. Just a note, we usually pick odd numbered Ks. That's the same reason why most like juries or judge panels are odd. because we don't want a split decision. You know, if we had 4 and 2 were this, 2 were that, what do we say? So we always generally pick an odd number. So then we have a clear decision one way or the other. Okay, questions on K nearest neighbor? So again, we have an out there. I don't even know how the code actually does this. This is the model that does this. It can't be too hard, but there's a one-line code for doing this once we get into doing it. So, and we just say find whatever, we specify how many nearest neighbors we want. So, questions on this? And online people, feel free to type questions in the chat. I'll keep the chat up here. Okay. That's one way. Another way is support vector machines. Here we're really trying to draw a line through our data and separate our data with some line here. So again, the idea is that we have our data here and we want to try to find a line that best breaks this data up. And again, if this is what we call linear or separable, it's really easy to find a nice line here for this. We find the line and we put it in here, and everything on one side of the line will be one type, everything on the other side will be another type for this. There's a fair amount of math between determining this line. We want to find the line that's best. So what we call the widest separation here at the right angle so that we can separate things the best here for this. Now, in 2 dimensions, this is a line. You can just imagine in 3 dimensions, this would be a plane here. So like if we had things floating, there's like balloons floating all around this room and we had to separate them, we would draw a plane through the room. And all the things on one side of the plane would be one thing, and all things on the other side would be another item for this. So in 3 dimensions, this is a plane. And again, when we work with 20 dimensions, it's a multi-dimensional plane. It's really, we can't visualize it there, but it's always that way object. So, and again, we're trying to find, like, here's the different flowers again. And again, we can draw any number of lines to separate them, but we want to find the line with the widest alleys kind of here for this that separates this and at the right, and it sets an angle. So there's there's some math you can run to try out all the different or calculate what this line should be for this. Often we'll use linear lines, but you can use curved lines. Common way of doing it is what we call radial basis functions. Use curved lines here. We sometimes specify a parameter called C, which is how lenient we want to be when we misclassify a point. Let's see, I haven't checked out this link. Let me see if I can bring up this link here. So again, we want to find this large margin here. This walks you through the math of that, but let me see if I can get down here. Oops, I thought there was a good picture here of seeing it here. It must be somewhere else. Okay. So the parameter C helps us. Oh, I think that's in your exercise. Good. And C by default is 1 here, which is kind of, we want to keep all the items on their separate lines here, but as we increase C, we'll try to not to misclassify items. Where this tends to be a problem is that when we get away from linear lines into curved lines, we can make really fancy curved lines that kind of wrap all around the data. So if we looked up here, if we are trying to classify this data, we could maybe have a curved line that goes through here, through here, through here, and wraps back and handles this big curve here for some sort of a curved line. And do we want that kind of curved line, or do we want it less curved here? So we sometimes misclassify some data in our stuff. So it's fast, it's effective. Support vector machines are one of if you want a quick way to classify data, I would suggest support vector machines. It's my favorite of all these here. So, okay, let's go on to next, decision trees. And with those random forests. So a decision tree is a bunch of if-then statements where we try to classify. I always think of this, when I was your age, AI was taking over the world. That was back in the 90s. AI was taking over the world, and they're going to replace all the tech workers back in the 90s. And we were all going to be we were making expert systems. We were just going to have to, all we had to do is go interview people, find out their rules for determining them, and program those rules into the computer. So like if you're going to determine if something's tumor is cancerous, you just talk to a physician, a radiologist or someone who's expert on looking at tumors, and you'd say, well, how do you go about determining this? And they'd say, oh, well, if the radius, if it's this size, then I know it's cancer. But if it's not, then I look at this, and then if it's there, I know it's benign. If it's this here, I know it's this. And they walk you through those rules, and we have a little logical system. We type in those rules, and the computer will solve the world's problems with us. So that's what I was told when I was your age, that AI was going to replace all programmers and everyone, and that we were all going to do this. Didn't happen then. We'll see. We might be closer to that now. I don't know, but we're always saying that. So here's an example with the iris data where he first asked if the petal width is less than 8 centimeters, then if it is, then we know it's a setosa. If not, we ask another question. We look at the petal length. So basically what it's trying to do is, like, if we have this data here, we'll say if we can just draw a line. If the petal width is below this line, it's this one. Otherwise, we're up here, and now we'll say, well, maybe if it's the remaining ones, if it's less than this, it's orange. And if it's right than this, and we start boxing things out, with these things. So if the petal width is less than this, it's a setosa. Otherwise, we look at the petal length, and if it's less than this, we go down here. And then we say, okay, so we looked at the width. Let's look at, length. Let's look at the width. If the width is here, then we know it's a versicolor. Otherwise, if the width is more, we know it's a virginica. Here we go here, and we break it down some more. And breaks it down with a bunch of these if statements. So this is called a decision tree. The computer can look at the data and generate this tree for us. It is nice and fast. It is easy to explain to users. It's not what we call a black box. You can, someone say, well, how does it work? We go, well, here, we first do this and we do this, and it's like an expert ruling these out. So it can overfit the data with too many rules for this stuff. It sometimes doesn't generalize once well. So, maybe, again, we have this data here, and we are bringing in new data. So how we want a generalized solution that'll handle all the new data we're seeing here. So sometimes this is almost it doesn't generalize well sometimes. So instead of decision trees, we sometimes create a random forest. So again, you can just guess random forests from decision trees. We're going to make a lot of random trees, and we're going to put them together in a forest. That's our metaphor that we're working with here. So if this is one tree, we're going to generate lots of random trees and have them all vote on what the result is. So how do we get random trees? So rather than looking at all of our data, so every dot here, we will randomly pick half of this data and generate a tree, and randomly pick another half of the data and generate. And again, maybe it's not half, maybe it's 90%, maybe it's 30%. We'll randomly pick again, and there's different ways of doing this, but you'll randomly sample the data and generate a tree, randomly set the data and generate the tree again there. So we'll generate all these trees here. So each tree will make a vote. Like here, we generate 3 trees here. So we had our data set. We broke it up in each set part of it to 3 different trees. Each tree generated a different result here, and then the trees will vote on what is the right thing. Again, we often do an odd number of trees and like that, and we have them all vote, and whatever solution, whatever category gets the most votes, that's what works. And random forest works really well, works very fast, and so that is probably the top system. I like sport vector machines because I just like the math behind it, but a lot of people will prefer random forests. I think they just like think it's a cool name there. So. Now, so there's a website called Kaggle with data competitions here. And in these competitions, you can win some money. You can win like $50,000 if you are the top competitor. Well, actually, they break down the price. So the top competitor probably gets 30, second gets 20 or something. But you can add some money there. This has been going on for years now. Originally, you could just you could take that data, do decision trees on it or random forest, and you could often get the best prediction there. But then people got more competitive, and so for a long time they used what are called ensemble methods, because again, is a support vector machine better or a decision tree? So ensemble methods are ways of stacking or combining these methods together. So bagging is bringing in a bunch of similar models, training them independently, and have them vote for an answer. So like random forest is a bagging method that just uses decision trees. But you can also do the same thing for support vector machines, have a bunch of random ones of them and put them together. Boosting is like combining them. So let's use decision or support vector machines for most of the stuff, but then when we're not quite so confident, we'll use decision trees or something like that. So you'll combine them. There's complex methods of boosting your results or stacking your results. So for a number of years, the top winner, the people winning money in Kaggle competitions always used an ensemble method. That was the way to go. I remember when I first started teaching this and first started looking at Kaggle, every winner for every competition was an ensemble method. Okay, we didn't have neural networks very well back then. We didn't have deep learning, and so that was really common. So again, there's these ensemble methods, and a lot of the AI systems now have these built in to them. So they just use some combination of the other methods above. So, okay, questions on these? This week, we'll have you apply these methods to the breast cancer data, to the iris data, and the breast cancer data here. We'll apply those methods to those 2 data sets. Now let's look at something else that's not really classification, but clustering, and talk about what clustering is. So for classification to work, you need to have things with labels. You need to have a bunch of tumors and say, these are cancerous, these are benign here. But a lot of times we have data sets that aren't labeled here. A typical one is consumers. Here we have a bunch of consumers, a bunch of users, and we don't have them classified some way, as this is a sci-fi Netflix person. This is a children, or this is a someone who likes action movies. Oh, my wife likes watching. I don't know if she likes watching murder mysteries or things like that that have a lot of blood in them, and I just don't like blood there. So we have this. So there's a number of shows that she has to watch when I'm not around because of the blood. So again, because that's not on, I'm not labeled as no blood here, kind of in my Netflix profile. But we want to be able to cluster or organize people that way here. So we'll talk about this sort of stuff, clustering here. Again, we might have, a lot of exoplanet observations. How do we don't know much about the exoplanets, the planets outside our solar system, but we've been observing lots of them. We'll cluster them by what we've observed here. I remember doing a report on hospital and patient outcomes, just clustering hospitals and seeing what trends were there from similar hospitals based on their patient outcomes. How would you cluster different hospitals together here? And again, sometimes we find this association mining once we, related to this, where we'll put customers together and products, and this is the Amazon. You might also like this sort of stuff. Again, sometimes we'll try to group patients and related medical conditions. So patients with this sort of medical conditions will often have this maybe, and again, it may be a condition that you might not think was related to this. So if you have diabetes, you might also see this here. I just saw another, I think it was this week's Science Friday podcast was talking about proteins and protein sequences and using them to generate drugs for this. So again, trying to combine different proteins together and predict and look at protein stuff. Oh yeah, they were doing snake bite cures with protein generation stuff. So we'll look at credit card fraud here. Try to see that. I know people have looked at search for extraterrestrial light, SETI, radio signals here. So how do we do this? Common means is called K-means clustering. So again, the K means, the K stands for, will be any number. So we'll have to pick this K out and we'll look at K-means clustering for that. The idea of this is that if we have a bunch of data here and we want to cluster it, let's say we think this data clusters into 3 clusters, we'll want to try to determine what these clusters are for this. So we'll start by putting these, you can kind of see these bigger X's. Let me bring this up into a bigger screen here. Okay. So you'll see these kind of bigger X's here, the red one, there's a blue one up here somewhere, and then there's this yellow big X. These are called, and there's a black X inside. These are called a centroid. We'll randomly put these 3 centers of these clusters randomly on our screen in our data. And then we'll tweak where they are based on this. So first, we'll generate K random data centers. We call them the centroids here. And then we go through this step here. So the first step is that once we have a cluster, we will find all of our data points that are closest to that centroid and we'll mark them. So like initially there aren't very many ones closest to this purple one. But once we have those, then we'll move this purple centroid into the center of those that are classified as purple. And same with the yellow and the red. And then we'll redo it. Now that we've moved the cluster center, we'll recalculate which ones are in that cluster, and then we'll move it so that the center is, again, in the middle of that cluster. And so as we do that, the cluster's centers will move, and we'll kind of divide this up into parts with this algorithm. I think it's a cool algorithm for trying to cluster this data here. So we'll work through that and some clustering techniques. We do have to figure out how much clusters we should have and where should the clusters be. So sometimes we'll run into problems with that. Let me see if like if humans are really good, if you look at this data set, how many clusters, how many circles or groups do you see? 4? Yeah. So that, and again, so we could ask if you would say that. And again, but if you're just seeing the numbers, it's hard to see that. We can see it visually here. So again, we would like these clusters like this there. And so there are different ways of doing it. Again, what we'll do is we'll pick some random centroids there. We'll calculate how many, which items, observations are in each cluster based on that are closest to each centroid. Then we'll move the centroids to match those here. We'll shift them over and then we'll again calculate again. So even though we pick some random clusters to start with, by the end, we have our clusters set at the center of each object here, each cluster. And again, there's some nice math that kind of does this. And so here's our clustering here. Now, we don't know, we can sometimes get wrong clusters. It doesn't always work perfectly. So here is a bad clustering. We have this cluster. We put the green cluster is one big cluster, and then we kind of split this cluster into blue and yellow. So again, depending on how it works, we don't always get the same result, and we don't always get an optimal result with this. And again, sometimes if we pick too many clusters, here we pick too many clusters, and so it's dividing some of these clusters in half. So how do we know that this is a bad, you can kind of see it visually. How do you know that this is, why would you say that this is a bad cluster here and this is a good cluster? What does that mean? How would we calculate that or, figure that out here? So one way is we can look at like how many other things are within, for every observation here, how many other things or how close are the 5 nearest neighbors with this, or are the 5 nearest neighbors all in this cluster here? So for most of these, the 5 nearest neighbors would all be in the cluster, and only some at the end would we see. So maybe only 2 or 3 would be that way. Where here, this is not a good cluster because there's lots of observations here where the 5 nearest neighbors or some sort of measure of like that token might be. We can also maybe measure what is the relatively distance from every object to another object in the cluster. So every object to every other object, what is that distance here? Or every object to objects in another thing, is it far away? So we'd like the distance from every object to the other classes to be far away. So like this one is far away from here. This one is far away from here. But like these two are very close. They're in different clusters, but they're very close. There's some ways we can maybe calculate those distances. We're going to look at that sort of stuff here. So one thing we need to determine is how many clusters do we think our data has? And again, sometimes we can just see that, but a lot of times we won't be able to see that. So we have to ask ourselves that. So we will calculate this elbow method. This is kind of like the squares of the distances of all the objects in that cluster. And we notice that as we increase clusters here, this distance drops. So here, but at some point as we increase the number of clusters here, so this axis is the number of clusters. So with only 2 clusters, there's still a lot of distance between them. With 4 clusters, there's not that much distance between all the items in any cluster. That sounds pretty good. At 8, there's this much distance. If we add to 14, that distance, it hasn't shrunk very much here. So at this point, we're not getting much benefit from adding more clusters because the line's very flat here. So what we want to do is look along this curve and find kind of the elbow, this, right? That elbow in the curve here, and that will tell us how many clusters. So in this case, I would say, maybe 3, 4, or 5, somewhere in that range would be the right number of clusters there. So maybe we'd settle on 4, I don't know, 3, 4, 5 are all in that range where, again, at 3, adding another cluster helps, shrinks the distance quite a bit. Adding even 5, adding another cluster shrinks this distance quite a bit here. So somewhere in that range. So one way is the elbow method. We plot how many, the number of clusters and calculate this distance here. Another more complicated method is what's called a silhouette method here. So here's all of our clusters here. And again, we try to figure out some measurement of how many items are within are closer to this cluster center than another cluster center here. So here's our different clusters: orange, green, blue, black over here. And some of them are very good, like the blue cluster. That's a really nice isolated cluster. See, it's all very high. It's all above this red line. This, what we call the silhouette coefficient, is really high for all the values in that cluster here. So this is a very clear cluster. Even the green cluster is pretty clear. It's pretty high. And the black cluster. Now, this, let's do the orange cluster. The orange cluster isn't very good. Maybe see if I can bring that up a little bigger. So the orange cluster is not that great because there are a lot of items that are very close. That are closer to 2 than to 4 here. And you'll see that. See this cluster? It doesn't go as far to the right. In fact, part of it even shrinks down to the negative, meaning that some of the items are closer to the second cluster, to the 4th cluster for this here. In average, it draws this dotted line to average all the values here. And we want this dotted line as high as possible here to see good clusters. So we'll often do this for different values. This is for 1, 2, 3, 4, 5 clusters. We can generate this for 6 clusters, for 3 clusters, and kind of compare this for different number of clusters here. So, now, again, if you want, you can look at the code for this. I'm not going to spend too much time on the code, but let's just walk through this. Let me get rid of this. I just want to kind of show you what the code would look like. Again, this is a Python notebook. We're importing a bunch of libraries, and now we're importing just not just Panda, NumPys, and our graphing, Seaborn and Matplot, but we're using something called scikit-learn, which has like support vector machines and clustering, k-means clustering and stuff like that here. It also has things for scaling and splitting the data, which we'll see in just a sec. Okay, so now we bring in our iris data. Remember, we have sepal length, sepal width, petal length, petal width, and the species. We're bringing that in here. We're then scaling the data here, and then we're doing this k-means clustering. Some of these algorithms work best if the data is scaled. And then this is all we have to do. K-means clustering with 3 clusters here, and then we can then label it. And this is our clusters here. So again, we can do this. We can just specify as any, if we want to do this with 5 clusters, we could just as well. I could do this, or, if I want to do 5 clusters, I can just change that one line, and then I should be able to see the clusters with 5 different clusters for this. But again, how many clusters should we have? So we'll do the elbow. Here's the elbow data, and there's a pretty strong elbow right at 3. Here. So this looks like 3 is a good value for that. And we know there are only 3 iris species, so that would make sense here. So we can also do the silhouette analysis here. And again, we can do that. Let me see if I can get this here. We can do the silhouette analysis for 2 clusters, for 3 clusters, for 4 clusters, and 5 clusters. And again, we're watching this red line. We want this red line as far to the right as possible. And when we get up here to too many clusters, it's not that far to the right. It is actually further to the right here. This looks like a good clustering with 3. It actually works best with 2 clusters. If you remember the flower, I heard flowers. There's one species that was all by itself, and the other 2 were kind of all intermingled. So it actually clusters better with 2 clusters if we look at it. So, And again, this is complicated code. I don't even know how this code works. It's just published on the internet here for doing this kind of silhouette analysis here. And I think you can specify how many clusters. So the only thing I would change here is I could say, do it for this many clusters here. And it just, one of the things that just prints out also, besides the graph, is the values. And you can just see 2 clusters is 6.2. That's a much bigger than all the rest of these. Okay. Here's another example of clustering. We had faculty here that were going all over, well, to Hawaii and Alaska and places like that, and doing samples of water in little pools and little swamps and stuff like that, and then doing DNA and figuring out how many microorganisms were in this groundwater samples. Oh, not in ground, well, yeah. Surface water samples. And they had all these DNA matches, and they asked us to see if we could see some sort of combination of it. So again, we had the locations, every location. This was a fish pond in this spot, in lava rocks, and in this one. And so we had all this stuff, and we had information, but then we had the number of each one of these is a different microorganism. I know biology has such creative names for the microorganisms. So each one of these, so we can see, and we had no 307s in these samples, but in this sample we had an 813, but nothing else here. All of these samples had a 13422 in it, but different amounts. So based on what we're sampling, we're going to try to cluster these locations and see how it clustered for that. And again, we had no idea how many, how to cluster it, what kinds of clusters to do. So again, we did this plot, and we're saying probably 4 clusters, 3, 4, 5, maybe even 6 clusters for this data. And again, we could do silhouette analysis and ask the same thing. Here's our clustering with different number of clusters. This is looking like pretty good clusters. And I look over here, this is looking like pretty nice clustering for the data. In some ways, this doesn't look quite so good. So again, we're doing cluster analysis for this data. Okay. Oops. I'm not a very good business person. A lot of the cluster analysis is actually done in business to cluster customers and stuff. There's so much written out there on clustering customers and grouping. I mean, just look at your social media feed and how they determine that. I mean, your whole social media feed is cluster algorithms. They look at what you've watched and what other people have watched and cluster you in different groups and predict what videos or what feeds you'll want based on that. So I'm sorry I didn't do that, but there's so much written on that already out there. So if you are interested, and one of the things that's interesting is that at the end of this class, you can do your own little, you have to do your own little research project. So if you're really interested in clustering or prediction algorithms for social media, you can certainly do that then. It's really hard to condense a whole 20 years of stuff into one class here. Sorry about that. I've been talking a lot. I won't talk as much on Thursday because again, you'll be doing this sort of stuff here. Also, just so you know, for the project this week, there are 2 alternatives. The breast cancer one is a classification problem, again, where you are using these support vector machines, comparing that to decision trees, comparing that to a random forest on the breast cancer data. So it's classical, again, classification algorithm. The other one, credit card fraud, is one of these clustering ones where you're looking at credit card statement. You always wonder, like, do you ever have some sort of weird statement and your credit card people will call you up or message you on your phone saying, it looks like are you in Iowa spending $4,000 on cows on a cow today? And you'll say, yeah. Doesn't everyone go to Iowa, drive to Iowa, fit for this? And I was on a cow. Oh, no. So, they'll ask you something like that because they'll look at it and it won't fit your pattern, your stuff. So you can do, if you're interested in clustering, you can actually do the credit card fraud one. So you'll choose one of those two options. So I've never gone to Iowa to buy a cow. I just made that up. I don't even know if you can do that. So, not saying I haven't gone to like North Dakota to buy a cow. Okay, let's see. Let's talk about this whole pipeline of how this works for classification methods here. And again, we'll see this a lot going forward for the next few weeks, like 5-6 weeks. Our notebooks will tend to have this process. We'll import our data and we'll store that in some data set. We'll then clean the data. That's what you did last time. We'll often scale the data or normalize the data here. One problem with these algorithms is sometimes you have different measurements that aren't tied together so well here. So you might be measuring like the size. Let's say we're classifying apples, fruits, or apples or oranges, and one might be the weight of it in kilograms. So it might be like 0.4, something below 1 for kilograms for how much this fruit weighs. And another thing might be a measure of the circumference of the fruit, and that might be in millimeters. So that might be 300. So one of the measurements is 400, and the other one is less than 1. And a lot of our algorithms prefer these to be kind of in the same range there. So we will tend to scale or normalize the data, often between 0 and 1 for this. So we'll look at the whole data. We'll divide every item of data by the biggest one. So the biggest one scales to 1, and everything else, it's basically the fraction of what percent of the largest value each one is what we often do. And again, there are very easy methods for that, where we just say, take the data and we say, scale it, and it will scale all of your data for it. So then we have our clean data set. And again, we might be removing null values and other things. So we have a clean data set. Now we're going to have to train or break the data into their inputs and our outputs. So this would be our category often. What are we predicting? And this is our input. So like with our iris data, this would be the petal width, the petal length, the sepal width, the sepal length would be our 4 inputs. And our output would be just the species, or Tosa or Virginica. Or like with our cancer, I think we had 31 different measurements as our inputs, and our output was simply the 2 categories, benign or malignant here. So we'll break it up into that. Now, later on, we'll see more complicated outputs where we're actually predicting some numeric value or something like that here. So, or creating an image, outputting an image here. So sometimes this gets more complicated than we're just doing classification now. Okay, so now we have our inputs and our outputs. Now we're going to break it in. We're going to put like 90% of that stuff in what we call our training data to train our model, and we're going to reserve some of it for testing out here. So we're going to set aside like 10% of our data here for testing, and then the rest, the 90% of data, we're going to put into training. We're going to train our model. We're going to figure out where the support vector machine line should be, or where this works. We're going to train our model, set up our model with this data. So now we have our model, and now we have our test data, and our model can make predictions. So now we're going to take each of our test inputs, X's, and see if it predicts the right result. And from that, we'll get a score, and we'll say, from our test data, we are 90% accurate, or 95% accurate, or 47% accurate, or something like that here. Because most of these models will do really well at the training data. And we'll also look at that. We'll say, well, with the training data, we are 99% accurate because we know all the training data. It's kind of like, let's say you had a way to predict what car I was holding here. And first, I showed you all the cards. And then, and I showed you a card and say, can you predict what card that is? And you go, well, yeah, that's the Queen of Spades. I can see it there. So if you've seen all the cards, it's easy to predict them. So what we're going to do is we're going to reserve some cards so that we're going to see how well you're doing predicting cards. And then we're going to show you a new card and say, well, what do you think this card? You've never seen this card before. What do you think it is? And see how well you predict it. So that's kind of our general process for managing our data. And we'll see that in all of our notebooks going forward. If I jump ahead to Thursday, we're going to do this iris classification data, and we'll see kind of the same thing here. Well, we import our libraries, but then we bring in our data, and again, we're going to then take our data and break it up into training data and testing data here. So we'll break it up into training data and testing data. And then once we have that broken up, we'll train our model here. And usually it's a command like this called fit. So we create our model and train it, and it just sees the training data. And once we get that training data, then we'll have it look at all the test data and get a score. So our score will be on the test data. In this case, it's 53% accurate on the test data for this. So again, that's kind of what we'll see in our data is that process go through with just a few lines of code, hopefully. Okay. Let's talk about categorical inputs. Our model, we want numeric data. And so lots of stuff is numeric data already. Even things like you might not think of, like images are numeric data. We have pixel values there. We have a lot of stuff that's already digital, but a lot of stuff isn't. So like the month of the year, like horse, cat, again, we'll be doing one where we're trying to figure out how long it'll take these animals at the shelter to be adopted. We'll predict that. So if you have a cat at the shelter, is it going to be adopted or not? So again, or a cow or a hamster here. So we have these different things like this. These aren't categorical. I mean, these are categorical. They're not numerics. How do we convert these to numbers here? So one way, some of them are what we call an ordinal. They have an order to them. So for example, the months of the year, January, February, March, April, December, they go in order. And so we have, and again, you're well aware of this, January is 1, February is 2. So we have assigned a number to each one of them here. So that you know that since January is 2 and March is 3, those numbers are very similar to each other. They're closer to each other. Where March and October are different numbers, and so they're further apart. Now, this is a little confusing where one thing what breaks is that it repeats. So December and January are actually closely related to each other in the year, but their numbers are far apart. So that kind of doesn't help our system. Grades are again, similar. So we say an A is a 4.0, a B plus is a 3.3, a D is a 1. So again, we can assign a meaningful numeric value to these. But it doesn't make sense to assign numeric values to turtle and hamster here. Turtle and hamster, one's a 3 and one's a 4. So the computer's going to think turtles and hamsters are nearly identical. They have a lot of the same needs and wants and adoption rates and stuff like that. And I don't know if you go to shelters and try to adopt turtles and hamsters, but they're not that similar. And the people who adopt them are, they're whole different things. So they shouldn't be 3 and 4. They should be different there. And again, how do you even measure that? How do you say, how close are dogs and horses together compared to dogs and turtles? What does that even mean? So this is called categorical data, not ordinal. There's no implied order here. So we will not do it this way. Instead, we use something called one-hot encoding, and we'll use this a lot here. One-hot encoding is also sometimes called dummy variables. So what we'll do is we'll take this one column, pet species, and we'll break it up into a column for each possible answer here: dog, horse, turtle, hamster, cat. So this one item is a dog. And so this row is the dog row here. And so there'll be a 1 under dog. 0 means it's not a horse, it's not a turtle, it's not a hamster, it's not a cow, and it's not a cat. So, and then if we have a horse, it'll have a 0 for dog, a 1 for horse, a 0 for turtle. It's not a hamster, it's not a cow, it's not a cat. And again, one-hot encoding means that for each row there, it can only be one thing there. So you're either a hamster or a cow. You're not a hamster. What would you call a hamster cow mix? Well, we don't have we don't have any. What do you call those? Chirons? What's the term for like a griffin or something like that? Yeah. Okay. Yeah. So yeah, something that's a mix of species here. So it's one-hot encoding here. So if this is our data, we have a pet name, a pet height, a pet width, and a pet species. We'll change this, and we'll change this pet species. So now we'll have a pet name. So Scooby is going to be height of 45, weight of 125. Scooby is a dog and not a horse, a turtle, or a hamster or cow. So Alvin is obviously hamster. We're going with hamster with that. Okay, so Alvin's a hamster, height, weight, not a dog, not a horse, not a turtle, hamster, not a cow, not a cat. So again, this is what's called one-hot encoding for this stuff. Oh, Raphael's a turtle. Is that from Mutant Turtles, right? Did you guys grow up do you guys even know what Teenage Mutant Ninja Turtles are? Some of you do? Oh, good. It makes me feel not so old. There. So, I was at some kid's house and they were watching Scooby-Doo. I can't believe that someone today knows what Scooby-Doo is. I would have never guessed that because I watched Scooby-Doo when it was like new. So, okay. Okay, so we can have these dummy variables. It can't add a lot to our data set, so we have to watch that. So, for example, there are 3,000 counties in the United States here. There are 15,000 towns. So if you just have someone's address and you wanted to one-hot encode that address, you could have 18,000 fields just for each person's address. That's not going to be enough. And particularly if you have combinations. So if you're running code a medium blue t-shirt versus an extra large red sweatshirt, you could have thousands of different combinations of those values. So you do have to watch that process here. So, and we'll give you some practice encoding animal stuff because we'll start prepping for our this week for our animal adoption challenge, which I think it's next week. So okay. One other thing I'm just going to point out, but we're not really going to do, is talk about dimensional reduction here in principal component analysis. Sometimes, again, we end up with data with lots of dimensions and we just want to reduce it, often just even to draw a picture of it. And so what we'll do is take this data that's lots of different dimensions, like let's say the breast cancer data had 31 dimensions. A lot of them are very related there. So the width of a tumor versus the height, I mean, all these tumors are about the same size. So if it's a big tumor, both are going to be big. If it's a small tumor, both are going to be small. Do we need both the width or the length? Could we have some combination, some average or something like that? So PCA does that mathematically by combining these again. It's really cool. There's some links in here. We have a whole notebook looking at running PCA in different things here. if you've done math and you know what linear algebra is, it's really cool math between eigenvectors and perpendicularity. So PCA is actually finding the eigenvectors in a matrix of data there, and then rewriting the data with as using those eigenvectors for that. So there's really neat math involved in that here. So just so you know. But again, if you ever have a large, big data set and you want to try to condense the vectors out, and again, you will see a lot of times when I haven't even shown, when I'm showing pictures of stuff on here, I will use PCA to reduce the number of dimensions down to 2 or 3 so that I can actually graph it on the screen. Okay, what are we doing this week? So normal stuff. So you have an explore activity. So we have, again, these are all kind of general or looking at some of these things. So Microsoft has a set of find the best classification system with their automated stuff. A lot of these tools now are, rather than having you pick between support vector machines and random forest, they'll try them all out in their model and then tell you which one's best. Google has just a little course on decision force, what I call random forest, but they're calling decision force. Now, I'll just note, remember, you're supposed to spend under an hour on these things. And so Google says their course is going to take you 2 hours. So I would say you can get through the first 3 lessons in that time. Here's this Python data science handbook. This is a reading thing. So if you'd rather read, that's fine. And then here's a couple YouTube videos that I find helpful on this stuff, talking about this. So again, you can decide. And on each one, what activity you did, something new that you learned, something old you already knew, a quote, and a question. You have to provide that for each of these, whichever one you choose. Not for each of these, for whichever one you choose. So Thursday, we'll be walking through this iris classification stuff. Here's a bonus activity. Again, we used to walk through this k-means clustering. We don't anymore. So if you want to go through this project, you can. Bonus means that you can earn points on it, but it'll just help your grade. It won't hurt. So you can skip it and it won't be part of your grade at all. It doesn't count towards like the total points in the course. So in Brightface, I can just mark it as bonus, means it doesn't add to the total points for the curve. But if you do it, you'll get points there. So the discussion this week is on bias here, talking about bias in data and how it impacts ideas. So I want you to find some resource, watch a video, listen to a podcast, anything like that on bias. These are, again, some of you may have taken the CIS principles class. We talk about bias in there. For this, like Joy does a lot on bias in facial recognition. She has some excellent YouTube videos on that. She's still at MIT. I don't know where she is now. There. Nova did a whole thing on crime and how algorithms have been used to propagate the racial bias or different biases that we already have in our criminal prosecution system there, and how some issues and how we can maybe address that. So figure out that one of those resources, watch one of those, or again, I'd rather you can also I'm actually looking for new ones, so search something like that and post. Again, remember you have to do 2 postings at least. They can be original postings or reply postings here, and you have certain requirements for both. So, and again, the project's not due till next week. But this is actually a project you can actually start this week. This project, I mean, it only covers what we've been covering this week here. So you can do either of these and you can start them now. So that's our plan for this week here. Now, I'll just note that next week I'm going to be out of town. Here, I'm going to be out of the country. And so I'm thinking right now of just pushing this class online for next week. I was thinking about having a substitute in here, but didn't know how useful that is. So I'll make sure you have videos related. So we'll just next week we won't on Tuesday and Thursday we won't meet in class. We'll do everything online. I will be accessible online at least part of the day. So you feel free to send me emails and I will be responding to that if you get stuck here. Oh, and I have to post the TAs. I haven't talked about the TAs for this class. So we have Allie and Heba TAs for a couple classes, but they're also they'll help. They're also helping and doing TAs with that for this class too. So I'll make sure I post that stuff here for that. How'd it go today? Tired of me talking at this point. So, okay, let's wrap up there. Online people, any questions? Okay, I'm going to stop sharing and stuff. I'll stick around if you have questions. If you want to work on the activity, you can, and we'll start the want to work on the explore activity, you can, and then we'll do the learning activity in class. Okay, on Thursday. Yeah.